Okay, so today I'm going over 8.3, which is talking about the inverse of a square matrix and shows how you can solve matrices using inverses. So for 8.3, the goals are to make sure that you guys can verify that two matrices are inverses of each other, that you can use Gauss-Jordan elimination to find the inverses of matrices. You can use a formula to find the inverses of 2 by 2 matrices, so that doesn't work for anything larger than 2 by 2. And that you can use inverse matrices to solve systems of linear equations. And I see a chat message. Okay, you cannot hear me. Okay, good to know. Let's see, what browser are you in? Sometimes you need to update your browser, or try Chrome or Edge if you are not using either of those. So I will just sit here and see if we can get Alstacia to get her browser working. Before I move forward, I can always edit this out. Okay, so it looks like she's going to leave and try to pop back in. So we'll see if that works. Okay, joining again. Just waiting. All right. Are you able to hear me now? I am talking. I will also chat that. Hopefully that is working. I will wait to see if you chat back. I've not heard anything. There is also a setting for moving your phone for audio. Okay. There's a phone number. Let's see. Okay, it sounds like you turned your microphone on. Can you hear me now?
Yes, I muted doing the phone thing.
Okay, perfect. I'm going to actually put my headphones in so I can hear you clearly if you have questions. Glad that we got that figured out.
Yes.
Sometimes, Blackboard sometimes doesn't, I don't know, it's very particular about what you use.
Yeah, I don't know what's going on with my laptop right here. It's like, what did I miss?
Yeah, I was like talking to him like, I don't know if you can hear me. I guess I'll just keep going. Well, you didn't miss anything important yet, so. All right. So moving on from learning objectives. Okay, so the inverse of a matrix. So the inverse is very similar to what we do when we're solving an equation. Yep. And she just accidentally hung up. All right. Welcome, Julia. Are you able to hear me?
Drop the call.
Okay. Yeah, and we just got somebody else joining too, so like, this is just fun. Okay, so if we have an equation, we're in the form ax equals b, where a and b are numbers, basically. So, you know, it could be like 2x equals 10 or something like that. So we solve equations that are in that form by dividing by the number in front of x. So we're dividing by a. And dividing by something is the same as multiplying by the reciprocal, which would be 1 over a if it was a number. So if we're dividing by 2, that's the same as multiplying by 1 over 2. And so if we look at, we have 1 over a. If you have something like a variable in the denominator, you can rewrite it with a negative exponent. So that's the same as a to the negative 1. And so I basically walked through that process here. If you have a, x equals b, dividing both sides by a or multiplying by the reciprocal. That would then cancel out the a's. And then you can rewrite it as x equals a to the negative 1b. The whole reason I did this is because this is what we do when we solve matrices. As we're going to use this inverse, which is taking our matrix A to the negative 1 power and multiply it by b. So when we solve an equation using matrices, we're basically using the same rules with regular algebra. We're just using it on a matrix instead. So when we have an equation with matrices, we use capital letters. So instead of lowercase ax equals b, it's going to be capital A, capital X equals capital B. So we use capital letters. And we solve that. And actually, I forgot to change. That should be capital X as well right there. So your capital X, we're going to use a to the negative 1 times b. So that a to the negative 1, we call that the inverse. Now, what's different with matrices is if you have an inverse of a number, it's just the reciprocal. But the inverse of a matrix is not the reciprocal. We can't just take the matrix and then take the reciprocal of every number in the matrix. It doesn't work that way. So that's one thing to that we have to pay attention to. The other thing is that unlike regular numbers where the order that you multiply doesn't matter, order does matter with matrices. So putting the inverse in front of b is not the same as putting the inverse at the back of b. So that order matters. And the inverse always has to be in the front. So we always have to put that first and then b. Then the last thing to know is that if you take a matrix and you multiply it by its inverse, and you can do that one in any order, those cancel out and you're left with the identity matrix, which has 1s in the diagonal and 0 everywhere else. So those are just some pieces, some important things to know about matrices. Yes, Julia, you have a question?
No, I'm sorry.
Oh, okay.
Still trying to figure this stuff out.
Not a problem. If you do have a question, you can go ahead and raise your hand, and then I can, I'll
I see
stop.
what that means now.
So, okay, so those are the little basics that you guys need, just some things to understand. First thing that we're going to do is we're going to verify that two things are matrices. So I actually put graph paper on the background here because when I work with matrices, I often do it on graph paper because it helps keep these things organized for me. So I was just going to do the same thing here. I wish the grids were a little bigger, but I didn't have that choice when I was making this. So to show that it's the inverse of A, so if B is equal to the inverse of A, so that means B would be equal to A to the -1 power, that would mean that multiplying B and A together will give us the identity matrix. And then just for reference sake, the identity matrix is where you have ones in the diagonal and 0 everywhere else. So if we're going to show that B is the inverse of A, we're going to be multiplying B times A. So we're going to be multiplying those two matrices together. And this is, multiply matrices is something that you need to do in one of the problems on the homeworks. This is going to be very good practice. So I've written my two matrices next to each other. And the way we do matrix multiplication is that we take a row and then you multiply it by a column. And you do it like element by element. So, oops, I'm in the highlighter. Don't want to be in the highlighter. So I'm going to set up my matrix. So I'm going to take the 1 in the first row. Maybe I should actually, I'm actually going to color code this. I think that will work really nicely so that you can see everything that I'm multiplying together. So we'll make that 1 red. We'll use green, blue. I've got an orange. I've got a darker blue. Hopefully I have enough colors. We'll just use a regular purple for that. Got a darker red. And then I've got a light green. So I'm just trying to color code those so you can see what numbers are getting multiplied by what. So it's the first row times the first column. So I'm taking the 1, the red 1, and I'm multiplying it by the dark blue 2. And then you're adding, and then you're continuing on. So in that first row of B, I have a -1. So then I'm going to take the -1, and then I'm going to be multiplying it by the dark red 1. So if I go back to my highlighter, I took this row and multiplied it by that column. So it's 1 times 2 plus -1 times 1. Then you do the same thing, but you're now going to multiply it by the second column. And this is going, you're going to leave a gap because this is going to give you your second kind of element thing. So I'm going to have that 1, and now I'm going to multiply it by my purple 1 that I had. Plus, and then I have my green, so that's that -1, and then the light green 1. So that's the first row times the second column, and so that gives me my second location on my matrix. So once you've written that, then we go back. I'm going to go back to my highlighter. Then we're going to do that with the second row and then the first column. So my second row, now the color got kind of messed up because of the highlighter, but it was a light blue for the -1 times my dark blue of 2 plus, and now I'm going to take the orange 2 and multiply it by the dark red 1. So if you're kind of following the color coding, you can see how the rows and the columns are kind of matching up. Once I've gotten that done, then I'm going to move on from the first column to the second column. So I'm still going to have that light blue, -1, and now I'm going to multiply it by my purple 1, plus, and then I have my orange 2, and I'm multiplying it by my light green 1. So that is how we do the matrix multiplication. So I'm just writing, I'm trying to color code those so you can see. And from there, then we're actually going to do the math there. So even though I have the graph paper, I'm not doing a very good, I'm trying to keep it straight. So I'm going to start doing all of my multiplications here. So I have, I'm going to start with the first row, first column. 1 times 2 is 2. And then -1 times 1 is -1. Then I'm going to move to the right. 1 times 1 is 1. -1 times 1 is -1. Then I'm going to go to the bottom row. I have a -1 times 2, so that's -2 plus 2 times 1 is 2. And then I have a -1 times 1, so that's -1. 2 times 1 is 2. Now we're going to add all of these together. So I have 2 plus -1, so that gives me a 1. I move to the right. 1 plus -1 is 0. -2 plus 2, that cancels out, that's 0. -1 plus 2, that adds to 1. And that gives us our identity matrix. So if you multiply two matrices together and you end up with the identity at the very end, that means that these are inverses. So we have just proven that these are inverses by doing this multiplication, because we ended up with the identity at the very end. Are there any questions?
No, ma'am.
None for me.
Okay. The matrix multiplication is usually where people mess up, so I wanted to make sure that I showed that clearly, because it's really easy to accidentally write the wrong number. So
I was just doing it backwards before.
Yeah, and if you do it in the wrong order, you're multiplying the wrong things together. Yeah, so that's one thing. Is at the very end of this, I'm going to have some links, and I'm going to email out the links tomorrow as well to websites that you can use to multiply these things for you, so that you are less likely to make a mistake, or at least you can use them to check your work, if nothing else. Okay, so we've got some language here, just to things to let you know that. So not every matrix has an inverse. If it's not square, if it forms a rectangle, then it does not have an inverse. And sometimes even ones that are square don't have inverses. So if it has an inverse, it's called invertible, or another term is non-singular. If there is no inverse, it's called singular. So this is just some vocabulary. So here are the steps for finding an inverse matrix. you have some matrix A, you write your matrix A, and then after it, you write the identity matrix. Then you're performing row operations. Your goal is to do Gauss-Jordan elimination to basically put it in row reduced echelon form. So that's where you have ones all in the diagonal. And when you do that, if it has an inverse, you'll end up with the identity matrix, like it's sort of moved places, so now it's on the left side, and then the matrix that is on the right side is actually going to be the inverse. So I'm going to just demonstrate this process so that you have an understanding kind of how this works. So use Gauss-Jordan elimination here to find the inverses of matrices. So we have a matrix A, 1, 2, 3, and 7. So our goal, we want to you start with A, and then you can use a little colon there to just kind of separate it. So you're taking your matrix A, and then you're appending I to it. So what this looks like is I'm going to write A, and then you can put like little dashes here, and then you put the identity matrix, which has ones in the diagonal and 0 elsewhere. So we end up with a 2-row, 4-column matrix. And our goal is to, I'm going to write this, our goal is that we want to make the matrix so that it has the identity matrix on the left, and then it's going to have numbers after my little dash. So that's our goal. So that's our goal for performing the Gauss-Jordan elimination. So the first thing I always do is try to eliminate the bottom left corner. So to do that, I need to get my top left corner to be a -3 so that I can add them together, just like the elimination process with matrices. So what I do is I show this work kind of on the side. So I'm going to multiply row 1 by -3. I'm going to add that to row 2, and then I'm going to replace row 2 with that answer. So that's how I kind of indicate that that's what I'm doing. So -3 times row 1, that's going to give me -3. And then I'm going to get a -3 times 2, so that's a -6, a -3, and a 0. So I'm just multiplying everything in that first row by -3. And then I'm going to put my second row underneath it. And then I'm going to add them together. So I get a 0, -6 plus 7, so that's a 1. -3 plus 0 is -3. 0 plus 1 is 1. That is going to be my new second row. So now my first row is going to stay the same. And now my second row is replaced with what I just did. So if you're looking at our goal, I'm almost there. 3 out of the 4 places match what I want, but I need to have a 0 in that top right. So to get to that 0 in the top right, what I'm going to do is take my second row, multiply that by -2, and then add that to the first row. So I will take my second row and multiply it by -2, add that to the first row, and then I'm replacing the first row with that, because I'm trying to get rid of that 2. So that's going to allow me to do that. So -2, and my second row has these values. So this is why I'm kind of writing them in different colors so it doesn't get too confusing. So when I multiply that by 0, I have 0, -2. Oh, I said I multiplied by 0. I'm multiplying by -2. -2 times 0 is 0. -2 times 1, I got a -2. -2 times -3, I got a 6. And then a -2. And now I'm going to write my first row on top of that and then add them together. So I got 1. The second column cancels. 1 plus 6 is 7. 0 minus 2, that's -2. So now that's going to be my new first row. So I have 1, 0, 7, -2. My second row is not changing. And when you write matrices, you have to have these brackets around here. So that's really important to make sure you're using those brackets. So now you can see that my left side is our goal. We have the identity matrix on the left. And if you can get to the identity matrix on the left, that means you have found the inverse. That means there is an inverse. So that is, so we have the identity on the left, which means that the matrix after that is the inverse. So the inverse of A, which is A to the -1 powers our symbol, would be the matrix 7, -2, -3, 1. Are there any questions?
Yes.
Go ahead.
Yes. Where did you get the -3 and -2 from?
The -3. Oh, how did I figure out to multiply by those?
Yes.
That comes from, think of it as the same thing as doing the elimination process. So my goal, so when I was looking at the matrix, I knew that I needed to get rid of this 3. So in order to get rid of that 3, I had to make this 1 be -3, so that when I added them together, it would be 0. So that's why I multiplied by -3, because I wanted those to be the same so that I could use elimination, basically. So I can add them together, and that would go to 0. So that's the same thing here. I needed to get rid of the 2, because that needed to be 0. So I knew if I multiplied this by -2, those would cancel. So that's where I decided the -3 and the -2. It's just like you're doing elimination. We're just not showing the variables, but with the same sort of steps.
Okay.
Does that help?
Yes, it did.
Okay. Are there other questions?
No, ma'am.
Okay. So, if that method confuses you, there is a shortcut when you have a 2x2 matrix, which is nice. So, this is, it's got lots of variables here. So if you have a matrix and just the numbers are going to be A, B, C, and D. So first you need to find AD minus BC. So basically you're multiplying one diagonal, A times D, and then you're subtracting the other diagonal, B times C. So that is what's called the determinant of a matrix. If that number that you calculate there is not 0, that means there's an inverse, and so you can go ahead and use the formula to find the inverse. If that comes to 0, that's going to cause problems. There are different ways to indicate a determinant. One thing that's commonly used is straight lines around the matrix. So you want to pay attention that they're not brackets, but straight lines. So when you are showing your work, make sure that you're using the right symbol, because there's a big difference between having brackets and having straight lines, because they mean something completely different when you have matrices. The other symbol for the determinant is just written det of A if the matrix is called A. That's usually what I do, as I indicate, okay, that's my determinant. So if this, oops, I forgot I was on the highlighter. So if we said this matrix is equal to A, then the determinant of A is that A times D minus B times C. So I just use that symbol, or I write it that way instead of the straight lines because it can get confusing. And usually if you're using like programming, like if you're using a calculator that does programming, things like that, they usually have some built-in thing that's a determinant and they use DET. So that's what I use for the determinant. But anyway, the formula to calculate is this for the inverse. So you're taking, basically you're finding the determinant and then you're finding 1 over that. So you're doing the reciprocal of the determinant. And then you're multiplying it by a new matrix. And the way the matrix is, you can see that the first diagonal, we're just flip-flopping where A and D are. They're just reversing places. And the second diagonal is just changing the signs. So I kind of try to remember this as it's a flip-flop and then you change the signs. And I just like, okay, this direction I'm flip-flopping them. This direction I change the signs. Just sort of my diagonals there. That's how I remember. So flip-flop, change signs. I don't know if that's going to help you guys at all, but that's how I remember it. So let's do this. And I copied the formula for the determinant up there so that we have that. So we've got the inverse of A. So it says if possible because not everything has an inverse. So the first thing we want to do is actually find the determinant. So just as I'm going to write this, the determinant of A again is A times, oops, D minus B times C. So my determinant of A, I'm taking the first diagonal and I'm multiplying 1 times 2. So that's going to be 1 times 2. And then you subtract the other diagonal, negative 3 times negative 2. So it's one diagonal minus the other. You have to make sure you're doing the subtraction in the correct order. So we get 1 times 2, so that's 2 minus, and then a negative 3 times negative 2, that's a positive 6. And that will give us negative 4. So that is not 0, which means that, yes, we have an inverse. So that means we can find the inverse, because that didn't come out to 0. And so if that came out to 0, you can see in the formula for the inverse, we would end up dividing by 0. So that's why there's an inverse as long as you're not dividing by 0, because that would cause a problem. So once you calculate that, then it's just a matter of filling in all the numbers. So we have 1 over the determinant of A, which is negative 4. So that's going to be 1/4, or negative 1/4. I can't miss that negative. And then I'm multiplying it by a new matrix. So I'm flip-flopping the first diagonal. So I'm changing those positions. And then I'm changing the signs of the other diagonal. I flip-flopped and then changed signs. Then what we do is we multiply everything by negative 1/4. So if you have a number outside of a matrix, everything on the inside gets multiplied. So I'm not going to reduce these right away. I'm going to just do the multiplication. So you'd have a negative 1/4 times 2, negative 1/4 times 3, negative 1/4 times 1. And so you end up with this matrix with fractions. And then you would reduce them. So we've got negative 1/2, negative 1/2, -3/4, -1/4. Unfortunately, a lot of inverses end up with fractions. That just kind of tends to happen. But that's it. That's your inverse using the formula. And you would get the same inverse if you use the other method that I showed to do the inverse, where you do the row reduced echelon form. Are there any questions on that process?
No.
Which process do you like better?
Not that one.
Definitely vote for the first one.
You also like that? That's, you know, I always do it the first method too. My problem is I have a hard time remembering this, and it goes faster, but like the first method is sort of what you're doing for solving anyway, so I feel like, well, it's just the same sort of thing. I already know what to do.
No.
But
Easier
this,
to follow.
yeah, the problem with this method is it only works if you have a 2x2. If you have anything bigger, it doesn't work. So it's like I might as well just use the first method all the time.
Yeah.
Okay, so now the last thing is how you actually use this to solve. Oh, and again, I'm having a problem with my capitalization there. So you basically, in order to use this to solve, you first find the inverse, and then you multiply that inverse by b, which is like if you have in a system of equations, that's the things that the numbers are equal to, or the equation's equal to. And that will give you your system, your final answer. So solve this system using inverse matrices. So the first step is to turn the system of equations into a matrix set of equations, basically. So our first matrix, A, is going to be the coefficients in front of x and y. So I have just the coefficients. So this is our matrix A. Then what we call the X matrix is the variables, X and Y. Usually when we work with matrices, we use X1 and X2 because it's an X matrix, so it's, you know, it kind of makes sense, they're all X's. But our system here was X and Y, so we use X and Y. And then what it's equal to, 0 and 3, that is our B matrix. So this gives us AX equals B. So the first step is to find the inverse of A. Now I'm going to do this using the method I just showed you with the determinant, because in this case it actually is much faster. So I'm going to just show that here. So I'm going to use the shortcut. So the determinant of A, we have my first diagonal, so that's going to be 1 times -3 minus the second diagonal, 2 times -2. So that gives me -3 plus 4, which is equal to 1. So if the determinant is 1, then if I go back to that formula, 1 over 1 is just 1. So basically, I don't have to do any multiplication. I just have to do the flip-flop change signs part. So that's why I'm doing this one that way, because the determinant came out as 1, and so it's actually really, really simple. So A inverse, we would just have 1 over 1 in front. And so now I need to flip-flop my first diagonal. So that's going to be -3 and 1. Change places, and then change the signs on the other diagonal. And then because it's just 1 over 1, basically we already have our inverse. So that's, in this case, it was pretty easy to get the inverse, and it didn't involve any fractions or anything, so that's quick enough. So once you have your inverse, your second step is to multiply inverse by b, and you have to go in that order. So I have -3, 2, -2, and 1, and then I'm multiplying that by 0 and 3. So this is a 2 by 2 matrix multiplied by a 2 by 1. So our result is going to be 2 by 1. When we're multiplying matrices, your result is going to be based off of the number of rows in the first matrix and the number of columns in the second matrix. So that's how I figure that's going to be, how that's going to work. So first row, first only column. So I'm going to have -3 times 0 plus 2 times 3. And then I'm going to have the second row times the column. So -2 times 0 plus 1 times 3. And so -3 times 0 is 0. So that's just 2 times 3. So I get 6. -2 times 0 is 0. So it's just 1 times 3, which is 3. And so this is our x, which we said was x and y. So if you look at it, right, x and y. So this tells us that our answer, x is equal to 6, y is equal to 3. And so we've just solved that system using matrices. There are questions?
No questions from me.
Does that make sense? Were you able to follow that?
Mm-hmm.
Yes,
Kinda
I think
makes
it's just
me-
a practice with this.
Yeah, some people love matrices, some people don't. I think I love them. I think they're kind of fun to work with. You don't really have to work with any of the letters. You're just multiplying and adding, and it kind of goes back to the basics of math.
Yeah. Seems a lot simpler than trying to find an ordered pair versus breaking down the equations like we did in our first assignment. I'm not gonna lie, I sat on number 2 for like 4 hours. I did, and there's a guy that lives with me that's in school, and he was like,
You can always send me a message if you have a question. You can even say, here's what I have so far. Am I on the right track?
Well,
It will save you time if you do that.
C. I got stuck on C. Not the whole problem, just C. And so seeing that, I'm like, bro, that's
It's like, oh, this is what I needed to do.
Yeah.
Yeah, now even better is technology, because the one bad thing about these things is that it's really easy to make a mistake with your math, especially if you have really large ones. Like if you have a 3 by 3, I will say, like problem 4 on the week 2 assignment is so much easier to do with matrices than to do it by hand. So these are all going to get emailed out tomorrow, but you are welcome to use any of these. So I actually like this one right here, the reshish. So I'm just going to click on that one, and it opened up on my other screen. So it actually has a graphing calculator as well. So there is an option for Gauss-Jordan elimination, and you tell it basically how big your matrix is. So let's say we have 2 rows, 4 columns, and you click set matrix. So if I go back to that one that we had, where we did that, like right here. So I'm going to put this matrix in the calculator. So luckily I also have this written down on paper, so I know what the numbers were. So don't worry about the x1, x2, x3b kind of thing. Just plug in the numbers as you see it. And then you click solve. And it didn't give it to us as a matrix. Well, that's not what I wanted to see. All right, let's try. Usually, let's see what the Desmos one will give us. This is why there's multiple choices here. Okay, two rows. We have 4 columns. Okay, let's try this here. See what it gives us.